Hi everybody, I'm Fabien Llobell. I'm a researcher for the Addinsoft society, which develops the XLSTAT software. And my co-author is Mostafa Qannari, which is from a university in France, Oniris. I will talk about cluster analysis in multi-block setting. So in the particular case where the data can be divided in several blocks of variables. So the data structures is several blocks of variables on the same observations, but the variables can be different from one block to other, and the number of variables can be different from one block to other. So where there are measurement of different types. So, for example, measurement of vegetation of a country, its wealth, the health of residents, with more than one variables for the vegetation, for the wealth, for the earth. And so we have one block by measurement type on the same countries. Another example is when there is a repetition of measurements. For example, the weather of each day. We can imagine the temperatures, the power of the wind for a different day or for different cities. So we have one block by day. And the last example is very classical in sensory data analysis. It's when measurements are made by different people. So where in sensory data, each participant gives their opinion on their perception of the product. So we have the product in rows, the descriptors in columns, to evaluate the products for each of the participants. And so we have one block by participant on the same product. A very small state of art for this kind of data. There is several methods for exploratory analysis. Some of them are statistics, general practice analysis, some multiple factor analysis. And the aim is to build a map of observations. For the cluster analysis of the blocks, Mostafa, Qannari, and I proposed the XLSTAT method, which is very useful in sensory analysis, since we have one block by participants. So the cluster analysis of blocks make a cluster analysis of participant, and the participant have several points of view for the products and the descriptors. So this cluster analysis allows to make cluster analysis for participant based on the several point of views. But our aim here is the cluster analysis of observation by taking account the multi-block structure. So we have the same observations for each of the block, so we can make a cluster analysis of this observation. For this problematic, we have an existing method. Nyang and Ouattara proposed to use a consensus clustering technique, which consists in 3 steps. The first is to perform a clustering observation within each block. Second is to choose a partition of each block, and finally to set up a consensus partition, which is achieved by the StatSC method. This method is really a good idea, but some drawbacks remain. The first is the fact that you have to choose a number of clusters in each of the blocks. So if the number of blocks is large, this can be problematic and time consuming for you. And the second is the computation time. Since we have one clustering algorithm by blocks plus one algorithm to find the consensus. So we propose a clustering method directly based on blocks of variables to avoid these drawbacks. The method, I will present the method, but first of all, I will talk about the pre-processing of the data, which is very classical with this kind of data, since it's double standardization. The first standardization of the variables of the blocks, which can be do or can be not for blocks. You can do that for blocks or not for another blocks. It depends on the scale of the variables. But a very important preprocessing is to set all the blocks on an equal footing. This can be achieved by standardizing each block by dividing it by Frobenius norm. And this standardization is very important, and I will explain you why after. Our method, the heart of our method is a minimization criterion that reflects the distance between an observation of a block and the cluster centroid, and we sum all the observations or the blocks on all the clusters. To minimize this criterion, we propose two algorithms. The first is a hierarchical algorithm. So at first step, each observation is a cluster. Each intermediate step consists to aggregate the two clusters associated with the smallest increase of the criterion. At that last step, all observations are the same cluster. And we can draw this hierarchical algorithm with a dendrogram, which is classical in clustering. The second algorithm is a partitioning algorithm that improves the quality of the clustering solution. It's so-called consolidation. We use the hierarchical result as initial partition, and after there are two steps which can be repeated. The first is in each block we compute the distance between each observations on the cluster centroid, and for each observation we sum the distance with the centroids of each block, and after we assign the observation to the newest cluster. And these two lab steps can be run until the convergence. An important property is that the total variation of the data is equal to our minimization criterion plus a so-called between cluster variation. So we have adapted finally, the reward criterion by propose a within cluster variation in the case of multi-block data. And this property allows to define an index for each block by computing the between cluster variation divided by the total variation. And this index reflects the fact that some of the blocks can be very well represented by the cluster solution, and some of the blocks not. Another important thing is the choice of the number of clusters. We propose two different adaptation of well-known indices. The first is the Artigan index, which is based on a ratio of two within cluster variation at different successive levels. And we can adapt this index by using our minimization criterion, which reflects the within cluster variation. The final decision is given by the number of clusters associated with the maximum of difference between the hierarchical levels. The second index that we have adapted is the Qannari index, which is based on the ratio between the between clusters variation and the within cluster variation at the same level. And so with the property, we can adapt this index, and the decision is given by the maximum of the Qannari index. As an illustration, we consider data which represents life condition in 540 cities and villages of Gironde, which is in the southwest and France. We have 3 blocks of variables: housing, employment, and environment, which different a number of variables for the different blocks. But for example, the 4 variables of environment are the percentage of land for building, water, vegetation, or agriculture. In housing, we have a variable like the density of population, which is not a percentage. So we have different scales in the various blocks. So the importance of the standardization of each block is very high. And moreover, if you just standardize the different variables of each blocks, since we have different number of variables in the blocks, the blocks which have a high number of variables should more contribute to the algorithm than the other blocks. So the standardization allows to resolve the problem of number of variables. The hierarchical algorithm results suggest us to cut in 3 clusters, even if the Qannari index suggests only 2 clusters here. And the partitioning algorithm consolidation imply a minimization that the minimization criterion decreases by 3% here, and 6% of comments change of cluster. Here, this is the index for each of the blocks. And we can see that the environment block is well represented here by the cluster solution, contrary to the employment block, whereas the environment has only 4 variables and the employment 9. So the standardization is again allows again results like that. I will talk about the special case of checkers that apply data. So checkers that apply data is a task very popular in sensory analysis. It consists to ask to each subject to check the attributes related to each of the given products. And so we have 1 block per subject, since we have the same products on the block, since all the subjects answer for the same products and the same attributes for each of the participants. And finally, this data is binary, since we have a 1 if the attributes has been checked by the participant and a 0 if not. As an illustration, we have 9 beers explained by 15 attributes per 17 subjects, and the attributes are situations in which the subject could see themselves drinking the beer. So, for example, at a barbecue, at rugby, at fine dining, etc. Again, I want to insist on the importance of standardization, since we have the same scale, same number of variables for each block, but some subjects tend to check a lot of attributes compared to others. So the subject must be put on an equal footing, and the standardization achieves that. The hierarchical algorithm results suggest us to cut in two clusters of beers, but the partitioning algorithm gives exactly the same results as the hierarchical algorithm. Here we can see the indices of each of the subjects. And we can see some subjects are very well represented by the cluster solution, and some subjects are not well represented. But there are 2 types of not well represented subjects. There are subjects which make different cluster of products, but also subject which not discriminate the products. I want to talk about the benefits over the usual method for checkers that apply data. So to cluster the products in the checkers that apply experiments, usually we compute the contingency table products time attributes. After we perform a correspondence analysis on this contingency table, and finally we use the correspondence analysis axis to perform a cluster analysis. But I want to show you a toy example with a problem with this method. So we have 5 subject A, so which have checked. We have put the they have put the product P1 and P2 together by checking the attribute A1 and A2, and P3 and P4 together by checking the attribute A3 and A4. Okay. We have four subjects which have again put together the product P1, P2, and P3 and P4, but by checking A3 and A4 for P1 and P2, and A1 and A2 for P3 and P3 and P4. And finally, we have just one subject like the four subjects B, which are not checked the attribute A2 for product PCAT. The contingency table is given here, and if we make a correspondence analysis on this contingency table, the results are that the product P1, P2, or P3 are placed together, but neither of the subjects have placed the product P1 with P3 or P2 with P3 here. So the cluster solution is not good here. And our method gives a good cluster solution with the skin of problematic data. So to conclude, we are introduced a clustering method of observation in case of data structured in several blocks of variables, which is based on an aggregation criterion similar to RAS criterion, since we've shown that we define a reason cluster variation for the multi-block structure. We've proposed two algorithms, a hierarchical and a partitioning, and we think that the two algorithms should be used one after all to improve the quality of the solution. We also adapted two of the well-known indices for the help of the choice of the number of clusters. We propose a quality index to see which block is well represented by the cluster solution and which block is not. We have investigated the benefits of the method in the specific case of Czechoslovak data. And finally, as perspective, we think by taking into account the multi-block structure, perhaps we could take account of specificity of some blocks, like blocks with categorical variables. Or we can apply specific clustering strategies to some blocks. So we have to change the minimization criterion for some of the blocks. Thanks for your attention.